Start recording. Right, so I'm going to share the PowerPoint presentation that I have with you. Before that, anybody have any questions, anything about anything that we did up to the past week or anything else that you need to know? Please feel free to ask. Right. By the way, there will be a second in-class examination for you, which will be somewhat similar to not similar in terms of the question, but in terms of the format, it will be somewhat similar to what you have done, in the previous exam. But this test will be go a little bit beyond in terms of the syllabus. What we will be covering, in this week, also can appear in the exam, right? So that will be somewhere within next 2 weeks, you will have that, right? So for that, be prepared for that. So let me take the right. Actually, I just put the chapter names for these lectures, but these are not, just like separate chapters, right? So that is just to keep an index for that. Otherwise, this is all this is about evolutionary process of the stars, right? And this last 10 to 11 lecture series, actually, it will be the same set of lectures that I did even in the last year students as well. So there is nothing much difference. Right now, let me share the screen again. Right. So you should be able to see my PowerPoint presentation by now. If you cannot see it, then please let me know, right? So otherwise, I'm going to start now. So this section is about what will happen to these high mass stars, right? So if you remember this chart right here, so we started like around 2 months ago, we started talking about how the process of the formation of the stars starting from a molecular cloud. There are certain conditions that need to be satisfied in order to form a star. Now, after forming a star, we call that as a protostar. From a protostar, all these stars will move on to move on as main sequence stars, right? Now, some stars will not have enough mass to go through this process, which we called as failed stars or brown dwarfs, because they do not have enough mass to burn hydrogen into helium or start nuclear fusion reactions, right? And then we talk about the stars that have a mass less than 8 solar masses, and their process we talked or discussed last time. It will become a red giant, and then the planetary nebula, and then will become a white dwarf, right? And then there is another possibility, which is that if a binary star, nearby star, combine with that particular star, there can be a type 1a supernova explosion, which we did not discuss last time, but I will incorporate that into this section, right? Because we are going to talk about the supernova explosions anyhow when we talk about high mass stars. Now, today, I am going to talk about these two sections, right? So what will happen to these high mass stars? So we will talk about the process of high mass stars, and then there is a final stage for these stars, that these high mass stars could become neutron stars or black holes, right? So that's a possibility at the end, which we will discuss again separately. But for now, this section we are going to start with this section, right? So I hope now things will be clear for you, because we are restarting after some time. But in this time, just to let you know, we will continue and finish all the lectures within, probably this weekend, and maybe some midweek days, and within the I just plan to finish everything by the end of the next week, right? There are around 8 lectures to finish. Right, now these high mass stage stars, you know that for the low mass stage, you do not have enough mass to make some of these heavy metals inside the star, right? Specifically at the central region of the star. Now for these low mass stars, where the mass of the star is greater than 8 solar masses, this should be actually a solar mass, right? So this symbol should be something like this. So make that correction when you have the notes. These notes are already available in the Google Classroom, right? So these high mass stars, they are able to burn their carbon in the cores, right? Remember, for the low mass stars, this fusion process is stopped when you have carbon at the central region of the star, because there is not enough mass to create the enough gravitational influence to contract the star and increase the central temperature in order to burn this carbon, right? Now what happens is, you have enough mass for the star. Because of that, they can pull or make these gravitational forces towards the central region and increase that in central temperature. So which means that you have carbon at the center, and then you can create enough temperature to fuse carbon into other heavy elements. So this is what happens for these high mass stars, right? So because of that, these high mass stars will not end up as white dwarfs. So what would happen is, they will continue to make these heavy elements at the center, such as neon, oxygen, magnesium, and silicon. Those kind of heavy metals will be created at the central region of these high mass stars. Now, as a result of this, you will have an onion skin layer of materials in the core region, right? And when the temperature increases with the depth in the star, you will have the successive stage will occur faster, and then you will have more heavier metals. Right? And so this is this onion skin layer that I am talking about. In the central region, you will have an iron core at the end, and in the outer region, you have the silicon, and then oxygen. Like that, in the most outer shell, you will have hydrogen. Right? So this is what we call as the onion skin layer. And at this point, the star will get larger and will become a supergiant star. What that means is, when the star will become larger in terms of its surface area, then what will happen is, the size of the star will increase. For example, now here I have shown that it can go up to orbit of the Jupiter, the size of a star, right? Remember that we have discussed about this previously as well. Right. Now, you know what the process, and there will be a point that this process also need to be stopped, right? So that point will be when you have these high mass stars end up with iron in their cores, right? So once the iron is made, iron is very special. That is because the iron is not being, its iron cannot produce any energy via fusion reactions. Now, if you remember the binding energy curve that you used to learn from nuclear physics, you should know that this iron is the heaviest metal that you can produce. After that, you cannot produce anything else, right? Because there will be no fusion reactions after that, according to the nuclear reactions. And because of that, this complete process of making heavy metals at the central region will end up at this particular point when you have iron at the central region, right? However, even the fusion reactions stop at the central region, the gravity will never stop, right? Because gravity doesn't have any, any limitation. It will keep contracting the star. So what that means is, you will have iron at the core. But however, the the force that you get towards the central region will keep increasing because the star will continue to contract, right? Because of the gravity. Now, this large mass and the high temperature involved in this particular process will make this process more violent, right, than earlier core collapses. So what will happen is, now you have iron at the central region, which means you cannot have any kind of fusion reactions after that. Even you increase the temperature because of the gravitational contraction, the temperature will continue to increase, right? So once this temperature rises up to 10 billion Kelvin, so there is something special that happens at the central region. So this will create photons that have extremely high energies, right? So these photons have very high energies. Now this, because of these high energy photons, they will have a special ability to break up these heavy elements such as iron in the core, right? And as a result of that, this will leave proton, neutrons, and electrons at the central region. Once again, what happens is you have iron at the central region, and then now you can have these high energy photons due to this enormous temperature around 10 billion Kelvin. Because of the interaction with these high energy photons with iron, so there will be a separate process that will go on, that these heavy elements will break up into neutrons, electrons, and protons, right? So this is a very special event, and you have a specific name for that. This is called photo disintegration, right? So that is the special name given to that, photo disintegration. Right. So this is what will happen at the central region of a star when the initial mass is higher than 8 solar mass, right? So I hope you can understand now. Now, as a result of this particular process, now you have electrons, protons, and neutrons at the central region at the end. Now, still the collapse will continue of this high mass star because of the gravity, right? So as a result of that, all these electrons, protons, and neutrons will be at the center, and the density will become very high at the end because of this collapse, right? Now, as a result of that, the electrons and the protons will start to squeeze together and they will form a neutron, right? So that is something special that happens here. So you have electrons, protons, and neutrons at the center because of this process called photodisintegration. Once that happens, still this contraction continues because of the gravity, and as a result of that, these electrons and protons are also squeezed together to form neutrons, right? So at the end, what we'll have is, at the central region of this star, you will have only neutrons, right? Now, when you have neutrons, these neutrons can generate the pressure. We call this as a neutron degenerate pressure, right? So what will happen is, due to this neutron degenerate pressure, this collapse of the core will suddenly be halted from these neutrons, right? And as a result of that, all the materials that are plunging inwards towards the central region will rebound back, right, at very high speeds. And this phenomena has a specific name called core bounce. And as a result of this rebound, this will create a powerful shock wave, right, which will blast through all of the materials surrounding the core, right? And this has a specific name. We call this process as core collapse supernova or type 2 supernova, right? And this is how a supernova explosion happens, right? So you probably have heard about this name, supernova explosion everywhere. And in terms of physics and astrophysics, this is what actually happens, right? So you should understand that. So once again, if I go back, for heavy stars that are more than 8 solar masses, you have all these heavy materials creating at the central region, and it will stop when iron is created. However, even after iron is created, the gravitational contraction will continue to happen, right? So because of that, you will have increasing temperatures at the central region, and as a result of that, you will have this particular process called photodisintegration, which will convert all these iron into electron, protons, and neutrons at the central region. And even after that process, this gravitational contraction will continue. And as a result of that, electrons and protons will combine to make neutrons. And at last, you will have a bunch of neutrons at the central region. So once you have only the neutrons, they are similar kind of atoms, and they will create a pressure called neutron degenerate pressure, right? And this neutron degenerate pressure now will stop this gravitational collapse, right? However, this process is somewhat is a violent process because of this huge amount of material involved. And because of the neutron degenerate pressure, what will happen is all these inward plunging materials will start to rebound back to the outward direction at a very high speed, right? And because of this violent phenomena, we call this as a co-bounce. And what will happen is there will be powerful shock waves generated, and this will blast away all of the material surrounding this core. So at the end, what will happen? This process is called, or this explosion is called the core collapse supernova or type 2 supernova. And after this supernova explosion, what we'll have is you will have this dense neutron core at the central region remaining at that place, and all the other material surrounding this dense neutron core will be blasted away because of this process, right? And this particular process is what we call as a supernova explosion. And actually, there are other type of supernova explosions as well. And this particular mechanism that is involved here for these high mass stars is called type 2 supernova explosion, right? So that type is important, right? Or core collapse supernova, right? So that is what will happen to these high mass stars at the end in a very brief manner, right? Now, still you can see that you have the supernova explosion, type 2 supernova explosion, all the materials will be blasted away, but that core with all these neutrons will remain there, right? So we will come into that point later when you talk about the neutron stars, because that is the starting point of a neutron star as well, right? Right. Now, so let's look at the other type of supernovas, right? Especially what happened, how these nova and supernova occurs for the low mass stars at the same time, because now we are talking about supernova. So what I am now talking is this part right here, right? Nova and type 1 is supernova, which we did not talk when we were talking about the low mass stars. Right. Now, so we all know that these stellar explosions are what we called as supernova explosions. However, we only talked about what happened to these high mass stars as type 2 supernova. Now, all these stellar explosions does not occur due to these high mass stars, right? So what we have just discussed a few minutes ago is as a result of an explosion occur in a high mass star, right? However, if you remember the white dwarfs that we talked last time, white dwarfs are also often become sites of explosions, right? But this process is very different. What actually happens here is when you have an isolated white dwarf, it will gradually become cool and fade away. However, sometimes there may be another companion star close by to this white dwarf star, right? So what happens is, naturally, if you have a close by star, due to the gravitational effects, the material from this close by star will be attracted towards the white dwarf, right? So mainly this will attract all the hydrogen gas that they have in the companion star, because companion star should be a normal star. So that means mostly you have hydrogen. So this hydrogen material will be attracted towards this white dwarf, right? So remember, this happens only if you have a nearby companion star. Now, if enough material builds up on the surface of this white dwarf by accreting material from the surrounding star, this hydrogen gas will start to ignite and undergo a thermonuclear fusion. Remember the thermonuclear fusion that we talked about for the usual stars. When you have hydrogen, they will become helium if the certain conditions met, right? The same thing will happen when you have enough matter built up on the surface of this white dwarf star. Then the particular star can go through this thermonuclear fusion, right? And this will cause the white dwarf to brighten very dramatically for a few days and then gradually fading back to normal. So this is due to the fact that you have these hydrogen fusion reactions, and these fusion reactions will emit huge amount of energy. And because of that, suddenly the white dwarf will brighten very dramatically, so that you can observe it very easily for a few days until it finished these fusion reactions, and then will fade away back to the normal conditions. And this particular phenomena we call it as nova. Actually, we don't call this as a supernova because there is no explosion, right? But this particular phenomena is called as nova, right? And so here is a system that depict what I have just mentioned. Here is the white dwarf star, right? At here, and here is the companion star. Because of the gravity, the companion star starts to give off its material towards to the white dwarf. So this material will build up around the surface of the white dwarf and will, spiraling, moving like that. And at one point, when you have enough material, they will go to this thermonuclear fusion to have this nova visible on the sky, right? Right. So here is such kind of nova that you see. This is called Nova Hercules, which was observable in 1934. In the left-hand side is when the brightness of the star increased in 1934. And then in 1935, in the right-hand side, when you look at the same star after a year, you can see that the star has become a normal star again. So it has gone through this process to have a nova and brightened up. And then once all the materials are over, fusion reactions are over, it has again came back to the same position as a normal star, right? So this is an example of a nova, right? Now let's move on to the other type of supernova explosions. Now this previous process is actually connected to this one. That's why we first started learning about the nova. And you can see here that if this white dwarf star that we talked before accretes enough matter from its companion, there can be much more extreme scenarios. So that means if the mass of the white dwarf increased beyond a certain limit by accreting matter from this companion star, there will be a different thing that can happen. There is actually mass value that it should increase. So this is again solar mass. If the mass of a white dwarf exceed 1.4 solar mass by accreting material from the surrounding star, it can no longer supported by electron pressure. Now, if you remember when we talk about the death of low mass stars in the last time, this what actually happens is at the end, these white dwarfs, star becomes white dwarfs and will become stable. That is because of the electron degenerate pressure. In the central region of a white dwarf, you have electrons, and these electrons create a pressure called electron degenerate pressure, which will balance the gravity, right? Gravitational collapse. And what will happen is, now if you have a companion star and has accreted enough material, and if the star go beyond this limit 1.4 solar mass, then what will happen is actually this electron degenerate pressure cannot support for this particular star, right? So the star will not become stable again, right? And there is a specific name for this threshold limit, 1.4 solar mass, that is called Chandrasekhar limit, right? And so the white dwarfs that exceed this particular mass will begin to collapse again. And as a result of that, this will lead to higher temperature, and this will cause ignition of carbon. You remember that for the white dwarf stars, what you had at the end is carbon at the central region, because there is not enough gravitational support to fuse carbon, it will stop there. Now what happens is, now you have a companion star which will give material to the white dwarf star, and if the material is not enough, then you will have a nova that we discussed in the last few slides. However, if you get more material and exceed the mass of the star beyond this Chandrasekhar limit, what would happen is, then you have enough mass to create this gravitational contraction to ignite the carbon at the central region, right? And what will happen is, when this happens, actually the ignition of the carbon will go throughout the entire white dwarf star, because this happens externally now. And as a result of that, the white dwarf will completely explode and totally annihilated, right? And this is what we called as carbon detonation supernova, or type 1A supernova, right? Now, keep in mind that we have talked basically about two types of supernovas, type 2 supernova previously, or that is also called as core collapse supernova, and that basically happens for high mass stars. When you have the neutron dense core at the central region of these high mass stars, the material is just that are coming towards the central region will be bounced back because of the neutron pressure created, right? So that is called type 2 supernova. And then we talked about the nova, which is due to the creating some material from a surrounding star towards a white dwarf. And this, if the accreting material increase the mass of the white dwarf beyond this Chandrasekhar limit, then you have a carbon ignition throughout the entire white dwarf, which will result in a complete explosion of the star, right? So that is what we call as the carbon detonation supernova, or type 1A supernova, right? So I hope now the differences and the similarities are clear for you for these different types of supernova explosions. Now we will actually talk a little bit about this type 1A supernova, because the type 1A supernovas are actually important in because of different reasons. One of the most important uses of type 1A supernova is actually they will act as distant indicators. So what that means simply is, these type 1A supernovas can be used to find the distances to different stellar objects, specifically for galaxies, right? Because, you know, if you need to find the distance to a nearby star, there are methods to use, right? So you can actually find the distances by using parallax method that we have discussed earlier. So stellar parallax methods can be used to find the distances. But when you go for larger distances, like distances for galaxies, you cannot use this parallax method because it will, the amount of parallax angle that they will create when the objects are far away will be very smaller, so that we cannot measure it, right? However, in that case, the supernova explosion, especially type 1A, will be a good way of measuring the distances very accurately. The reason is that actually the astronomers has found that when there is a type 1A supernova, the peak luminosity of a supernova has a certain value in laboratory frame, right? So once you know the peak value, then you can measure the peak value coming from a distant supernova and compare it with the laboratory frame brightness. And once you have the two brightnesses, you can actually use and this normal equation to find the normal equation that relates the magnitudes and the distances to find the distance to that particular galaxy, right? So that's what actually happens. So I have mentioned it here. If a distance to a faraway galaxy is required, one must first locate a type 1A supernova in it. So you have to locate a type 1A supernova inside the galaxy, and then you have to measure its observed brightness. Then you have to measure the brightness of that particular supernova, and comparing this result with the known maximum achieved by all such supernova, one can determine the distance to that interested galaxy, right? So that's how you measure the distances. And supernovas are extremely bright. Because of that, this method is useful for very large distances, up to 1 billion light years. So the advantage is you can go up to even up to distances like 1 billion light years, right, from this method. So this is why type 1A supernova is important, right? Remember that this does not apply to the other types of supernovas like type 2 supernova, right? Anybody have any questions up to here? So I will stop for a minute in case if you have questions. Right, seems like you do not have any questions, right? So let me then start from here. Now, in brief, what we have, discussed within this today's lecture is actually about the death of high mass stars, and at the end of this stage of the evolutionary process of high mass stars, which is a neutron star, how a supernova explosion occurred, especially about the type 2 at the first point, and then we now discuss about the type 1A supernova, which happens as a result of having a companion star into a white dwarf, right? Right, now we know how a supernova explosion occurs and the process and everything. Now the next question is, and also we have learned that the supernova explosions are very important, especially type 1A, to measure the distances to the galaxies that are far away. The next question should be, are these supernovas are rare, or are they happen more frequently? So according to the details that we have now, on average, we will have a supernova explosion occur somewhere in the Milky Way galaxy every 25 to 100 years. So for every 25 to 100 years, there will be a supernova explosion at somewhere. However, no supernova explosion has been observable in our galaxy since the invention of the telescope, right? So in that sense, it is rare, right? So either we have been exceptionally unlucky, or more likely recent explosions have taken place in parts of the galaxy where interstellar dust block the light from reaching us. So this can be due to two reasons. Maybe we are exceptionally unlucky, or we have recent explosions in the galaxy where we cannot observe those due to the interstellar dust that blocks the light, right? And also these explosions are very chance event. Because of that, there is no way to say that when the next one might occur, right? So we don't know when the next one might occur, right? And around the world, actually, these people are waiting for these supernovas and looking at the sky, because if there is a supernova, then you will have like a new star appear on the sky suddenly, very bright at overnight, right? That's how you detect the supernova explosion. Because of this huge energy release, it looks like there will be a new star suddenly appearing on the sky, right? So people are eagerly looking at the sky to detect this supernova explosion, so that they can make a little history themselves by finding supernovas, right? Right. So here is a Hubble Space Telescope image for the supernova 1987A. The previous details that we talked is about our own galaxy. Now this supernova is that happens at 1987. This actually happens at the Large Magellanic Cloud. Large Magellanic Cloud is the nearby galaxy for us. And here is an image that was taken, that particular galaxy. And so if I give more details about the supernova 1987A, this is a type 2 supernova, which means we cannot use it to measure distances, right? Only type 1A supernovas can be supernovae can be used for measuring distances. Now, this supernova was called SN 1987A, and this is by far the nearest and brightest supernova that we have seen in modern day times. And this was easily visible to the naked eye. And we have more details about the supernova explosions. This supernova explosion 1987A, and we have actually combined several theories and observations and reconstructed the life story of this particular supernova, right? So what we have done here is, for this particular star that create this supernova 1987A, astronomers have created the life cycle or the life story of this particular supernova. And so the details are, in the hydrogen fusion stage, it had a central temperature of 40 times 10 to the power 6 Kelvin. And the time spent in this space is 8 times 10 to the power 6 years, right? Now you can see that when you go down, you increase the central temperature, which is, you know what should happen because you create heavy elements. And at each stage, they will start fusing more heavy metals, oxygen, silicon, like that, until you have this core collapse at the end for this high mass star, right? And at the same time, just look at this time spent in each phase. Earlier, it's a longer time, but when you go through these different phases, the amount of time that it is spent in each phase become more less and less, right? So you can see that when it comes to the silicon fusion and then for the core collapse, it doesn't take much time, right? So it happens within a fraction of a second, right? So this is something that you have to understand, and you can connect this with your HR diagram. because HR diagram, we discuss how this evolutionary process happens, and you can, based on that information, you can actually relate this to that HR diagram as well. Just remember that we told that each successive process doesn't take that much time. There is another supernova that has happened in 2014. So this is actually a type 1A supernova. So it should be very useful to locate or find the distances. And this is located in Messier 82 or M82 object. And this is also called as the Cigar galaxy, one of the nearby galaxies. And the distance is here 11.5 million light years from the Earth. And this is by far the closest supernova of type 1A that we have discovered in the past few decades, right? Right. Now with modern telescopes, we can and detectors, it is now possible to detect supernovas in very distant galaxies, and thousands of distant supernovas have now been detected. So it is the nearby supernovas that we have not detected, but in terms of the amount of volume that we can look at, amount of galaxies, we have now detected thousands of distant supernovas, right? And many of these are billions of light years away from us. And these supernovas often rival their host galaxy in brightness, right? So if there is a supernova that is brightened up inside the galaxy, then the brightness of this star will be very comparable to the brightness of the galaxy, right? And we have detected both type 1A and type 2 supernovas. On average, what we can say is both type of supernovas are estimated to occur approximately once every 40 years per galaxy, right? And we know that the supernovas are extremely bright, extremely bright. However, they are only brightened for a few months, and then they'll fade away. However, they will leave some faint remnants. Otherwise, we cannot detect those supernovas now after this particular event. When it gets very bright, then you can detect that as a supernova, but it will only last for a few months and then it will fade away again. So if you need to detect that particular star where you had the supernova explosion, then you have to look at these supernova remnants. So that means what is remaining, right? So basically this debris from supernova can often be observed hundreds of thousands of years even later, right? So that is the advantage of having these supernova debris. So basically the expanding shell of glowing gas move outwards from the stellar core at speeds of several thousand kilometers, and this gas that moves outwards, you can detect normally, right? So those will appear as Crab nebulas. Now, for example, Crab nebula is a remnant of the Crab supernova, which was seen around 1,000 years ago. Now, this Crab supernova has occurred thousands of years ago. We cannot see the supernova now. However, we can see the Crab nebula, which is the remnant of the supernova, what is remaining after the supernova, right? Likewise, there are many supernova remnants that we can see even in our galaxy. Here are some examples. Right. So that is the end of that particular section. Before I start the next section about the black holes and neutron stars, let me know if you have any questions up to here. Right. So I guess all of you can see my screen, right? So I had a question asking which chapters will be coming for the ICA2. So this everything. I mean, you have to probably link everything that you have been studying up to today now, lectures that we are going to conduct even tomorrow, right? So that I would say up to chapter. This is chapter 16 or 17. I can't remember which chapter now we are looking at. So this should be basically there will be more focus about this stellar evolutionary process, starting that the place that we started to talk about the stars and beyond is what is more focused for this second ICA exams, right? So that will be, so I need to check the chapter number, but anything, the chapter that we started talking about the properties of the stars, and beyond that, everything that we are talking about the stars, even the lectures that we are doing today and maybe tomorrow also will be included, right? So our last section will be talking about the galaxies, maybe last 5 to 6 lectures. That will not be included. So that will come into the final exam. But for the IS2, it will be about these lectures that regarding the stars and stellar evolution. Right? I can't remember the chapter number, but I will check and let you know. Right. Now, in this particular section, I'm going to talk about neutron stars and black holes. Right. So that this is actually the very end stage of these heavy stars. However, these two topics are kind of little bit, popular among the public. So I thought, talk a little bit more about those. And if you remember, for the heavy mass stars, we discussed in the last chapter that how a type 2 supernova occur in a heavy dense star, right? So that is because of the core collapse supernova. Once you have this core collapse supernova, you have this dense neutron core at the central region, which is remaining, right? So everything else surrounding this dense core will move away because of this supernova explosion, right? And after that, for the heavy mass stars, there will be this dense core, which will consist of highly compressed neutrons, will remain as it is, right? And this particular object is what we call as a neutron star. So we give a specific name for that. You know that it's only neutrons there now. So this is called a neutron star. This particular star is actually not undergoing to fusion reactions like an ordinary star because it has full of neutrons. And as a result of that, these neutron stars are very extremely dense objects, right? And if you think about the density, if you take a typical, they are typically about 20 kilometers in diameter, but even more massive than the sun. So let's understand it in that you can think about 20 kilometer diameter, and then how massive it is, because it's more massive than the sun, right? So you can think about the density of that particular object. And this makes them a billion times denser than white dwarfs and 10 trillion times denser than the Earth, right? So you can see how dense these particular objects. Right. Now, these neutron stars are actually extremely smaller and faint objects. And because of that, their existence was very debatable for a long time because they are very hard to detect, right? And 1967, there was an astronomer using a radio telescope, and he detected an object that was giving off radio pulses of radio waves, right? So I'm going to make a connect. Now, what I'm trying to do is you need to I'm trying to give you the story behind the discovery of these neutron stars. And you can see the topic is not about the neutron stars. I am telling discovery of pulsars, right? However, these pulsars will be connected to neutron stars at the end. And so the people have discovered these stars that gives you objects that are giving off these rapid radio pulses. And they were even actually able to measure the period of these pulses, right? So this period has happening once every 1.337 seconds, right? And they are lasted for about 0.01 seconds. So you can see that there is something that giving off these radio pulses and lasted only for a very brief time. And you can see that this is a recording of a pulsar. You can see that there are increase in the intensity and then goes down suddenly like that. Pulses happens within a certain period, right? So it's a more regular one. Right. Now these pulsars first appear to be found in very blank places on the sky. So that means you just get the pulsar detected, but there is nothing seem to be visible in that region, right? However, later there was one pulsar found right at the heart of the Crab Nebula. Remember that I talked about the Crab Nebula in the previous lecture at the end. And what we know about the Crab Nebula is a place where you had one of these supernova explosion, right? So if that is a type 2 supernova explosion, then there should be a neutron star in that particular position, right? Because neutron star is what is remaining after this type 2 supernova explosion. And because of that, you can think that if you have a pulsar from a Crab Nebula, then this pulsar may be connected with the neutron star located at that particular position, right? And neutron stars actually have a strong magnetic field, which is capable of accelerating charged particles from this magnetic field. And as a result of that, there should be an emission of radiation. And that emission is what we are seeing as a pulsar, right? So neutron stars rotate very rapidly, and this is a consequence of the conservation of angular momentum. And if you need to understand this, think about, this is a very basic principle. You had a huge star at the beginning, and then most of the materials went away. Now you have a very small neutron star compared to the initial stage of the star. So the moment of inertia has lowered a lot. And because of that, the angular speed should be increased, right? In order to keep the conservation of moment of inertia, conservation of angular momentum. If you remember, when the momentum inertia is smaller, remember this, if I write, sorry. Remember this equation right here, I1 omega 1 equal I2 omega 2. So this is the equation wise equation for the conservation of angular momentum. So what happens is when the star becomes smaller and smaller, then what would happen is this moment of inertia will become smaller. In order to conserve the angular momentum, the rotational speed or the angular velocity or the speed has to be increased, right? So this is exactly what happened for a neutron star. And because of the loss of lot of material due to this type 2 supernova, the neutron star will rotate very rapidly. And this is a consequence of the conservation of angular momentum. And as the original star collapsed, so you have a conservation of angular momentum because the original star has collapsed. Now it's rotating very rapidly. And so there will be a magnetic field associated with. However, these magnetic poles are not aligned with the rotation axis. I will show you the how it works in the next image. And as the neutron star rotates, its magnetic poles may point towards us, appearing as a pulse of radiation. And this is what actually happens. And this particular image shows you the neutron star. And here is the axis of the neutron star. And however, the rotation axis is a different one. This is the rotation axis. The neutron star rotate around this axis. And magnetic axis is this one right here. And because of that, your beam of radiation will move on this direction, right? And here is another picture that gives you a clear idea. Here is the rotation axis of the neutron star, right? And then here is the magnetic axis. So because of that, beam of particles will move on to these two directions. And when this star rotates, what will happen is this beam of particles and radiation will sweep out like that. So when it goes through the Earth, then you will have the pulsar, right? And it will repeat again after some time, right? Now this is the connection between the pulsar and the neutron star, right? And this you can clearly understand from here that the pulsar can be a neutron star. However, there can be neutron stars that are not pulsars, right? Because you will detect it as a pulsar only this magnetic axis sweeps through the Earth, right? See what happens if the magnetic axis is in this direction. Then what will happen is you will not detect it as a pulsar, right? So that is something that you have to understand, right? So that's what I'm discussing here. Are all neutron stars pulsars, right? So the model of a rapidly rotating neutron star can explain the pulsar phenomena. As you could see, rapidly rotating neutron star is a pulsar. For a given neutron star, we will not detect it as a pulsar unless its magnetic poles happens to point towards us during its rotation. So that's what I am trying to explain you here. If the magnetic poles are in this direction, if the Earth is here, it's okay. When the star rotates, the radiation will sweep through the Earth, right? But this will happen only if the orientation for the neutron star is like this. So if the rotation axis is, somewhere in this direction, then your magnetic axis will go into somewhere like this direction, right? So then even you have a pulsar, we will not detect it, but the neutron star will be still there, right? So that's why we used to tell that all pulsars are thought to be neutron stars. However, the converse is not true, which means if you have detected a pulsar, that means there should be a neutron star there. However, that does not mean that that also means that there may be neutron stars that we are not detecting as pulsars. So that means all pulsars are thought to be neutron stars, but all neutron stars may not be pulsars, right? I guess the reason is clear to you, right? Actually, there are other methods of detecting neutron stars that I have mentioned here, because there are these pulsar phenomena sometimes seen at other wavelengths as well. And so I'm going to a little bit skip some of these, but skipping doesn't mean that they are not important. but I have sometimes mentioned all the points here so that you can read and understand it, right? And there are certain times that this ordinary star that is nearby will share a system with the neutron star, right? So this is an example of that. Here is the neutron star right here that goes around, and here is an ordinary star right here. And what happens is the binary, this is a binary system, right? So in this binary system, what happens is the material from this ordinary star will be transferred towards the neutron star. And as a result of that, this infalling gas from this nearby star will create beam of X-rays like that, right? And this beam of X-rays also can be detected, and so that is also an indication that there is a neutron star, right? That's why I told you there are other methods of detecting neutron stars, right? So that's the story about the neutron star, and actually there are some other extra details about neutron stars here, which I am not going to go through now, but you can go through and read it, right? So they are in the note. There's a small section about the gamma rays. Right. So anybody have any questions up to here before I briefly start talking about the black holes? Any questions? Right. So it seems that you do not have any questions up to now. So let me, so that previous section is actually about the neutron stars. And let me move on to the next section about the black holes. And I will slowly start this, and maybe we will not be able to finish it today. And if that is the case, I will take on it from the next day, right? Now, black holes are actually something, you know, it's kind of a popular topic that among the general public, and you may be also curious to know a lot of details about the black holes. Now, in here, what we are talking about the black holes is kind of in a more systematic way rather than just in a more popular way, because So we are talking about black holes because it's one of the evolutionary processes that could go through for a star, right? Now, when you talk about the black holes, in most of the 20th century, black holes used to be the stuff of science fiction portrayed either as a monster vacuum cleaners consuming all the matters around them, or as tunnels from one universe to the another. So there are a lot of stories behind these black holes, but you will understand at the end of this lecture that some of these stories are like just like made up stories. Some of there may be a possibility. So I'm not going to answer for those questions, but you will understand what actually happens and how a black hole is created, right? Actually, the truth about the black hole is almost stranger than these fictions, right? So we will continue our voyage into the universe and discover the black holes are the key explaining many mysterious and remarkable objects, including collapsed stars and the active centers of giant galaxies. So let's look at what are black holes, right? And here is a stellar mass black hole. Let's say a black hole. So what you have in the left is a visible light image that show a region of the sky in the constellation of Cygnus, right? So the region that you are looking at in this left-hand side image is an optical image. It's a region in the sky that belongs to the constellation Cygnus, right? And there is a red box that you can see marked. So that is the position of an X-ray source, which we called as Cygnus X1, right? So basically, when you look at that particular region, we have detected a lot of X-rays, and there is an illustration of that particular location as well. Actually, this Cygnus X1 that we have detected X-rays is actually a binary system, right? It's a binary star system, and which you can see in this right-hand side image. It's a binary star system like here. And so there is one star and there is another star that gives material towards the other star. And the material, what happens is once you give this material forms a disk around this star, right? So it is this disk that you see here. So there is a disk that forms from the material from the companion star, and so this material rotates around this black hole before falling it into the black hole. And so once this material is falling into the black hole, they will actually form a powerful jets, right? And then this material in the disk is very hot before they fall into the black hole. And because of that, they will emit X-rays, right? And you will detect these X-rays when you look at this particular object through an X-ray telescope. And detection of these X-rays what confirms that there is a black hole, right? So that's how we identify a black hole. So this is just an example of how we detect one way of detecting black holes, right? So so just to summarize it again, you have a black hole right here. So what happens is when you have a black hole, it's the huge place where you have a huge gravity, and because of that, the surrounding material will be attracted towards the black hole. So once it is attracted, these material will be spiraling around the black hole, and they will get heated up, and because of that, they will emit X-rays. And once you detect these X-rays, you can conclude that because of this X-ray emission, and you can detect those from X-ray telescope, that there is a black hole. So this is how you can detect a black hole. One way of detecting a black hole. Of course, there are other ways of detecting black holes as well. Now let's look at, having that in mind, let's look at the process of the formation of these black holes, right? Now we have seen in that some stars end up as white dwarfs and some of the other stars will end up as neutron stars, right? So that's what we have seen up to now. If you have a very low mass, less than 8 solar masses for a star, those type of stars will end up as white dwarf stars. And once you have these high mass stars, that are the stars greater than 8 solar masses, most of these stars will end up as neutron stars. However, there is one possible end state for these stars, right? So that particular end state is called black holes, right? Now, if you remember the neutron stars are actually prevented from collapsing by the pressure created these neutrons, and we called that as neutron degenerate pressure, right? So that neutron degenerate pressure prevented the collapse of the star because of the neutrons. However, if the star is very massive, the mass is very high, then this neutron degenerate pressure is also not enough to prevent the collapse of the star, because the gravity is now more stronger because of the huge mass that you have. And in this case, if you show it as a number, if you have a neutron star with a mass greater than 3 solar masses, remember now this is what I am talking here is only the neutron star, not the initial mass of the star, right? If you have a neutron star with the mass greater than 3 solar masses, then the neutron degenerate pressure cannot support themselves. These type of stars cannot support themselves against gravity. So that means the neutron degenerate pressure is not enough to stop the gravitational collapse if the mass of the neutron star is greater than 3 solar masses. It can be stopped only if the mass of the neutron star is less than 3 solar masses, and then this is where you have neutron stars, right? Now the condition is that if the mass of the neutron star is roughly greater than 3 solar masses, there is no way to support the gravitational collapse, right? So these objects will overcome the pressure from their neutrons, that is neutron degenerate pressure, and will collapse furthermore, right? So what happens is, now there is nothing to prevent the star from collapsing, because now remember for the lower mass stars, you had electron degenerate pressure that stopped the collapse. And then for the high mass stars, for a certain limit, you had the neutron degenerate pressure to stop the gravitational collapse. But when the mass is higher, so that you cannot stop the gravitational collapse from the neutron degenerate pressure, now the problem is there is now nothing to prevent the star collapsing in on itself, right? So this gravitation, there is nothing to prevent the gravitational collapse, right? Now what will happen is, as a result of that, this squeezes all the star's matter down into extremely tiny volume of space, because there is nothing to stop this now. So what that means is the density of the star will become extremely high, right? So this will be an unusually high dense star. And one consequence of these type of dense objects is that even the light is unable to escape from the inner region of this collapsing star. So you cannot have light escaping from this star because of this high density. And you will be wondering why. The answer will come to you when you talk about the next stages about these black holes. And these type of dense objects are what we call as black holes, right? And you can see, in summary, what has happened is, if the mass of a neutron star is greater than 3 solar masses, what will happen is this neutron degenerate pressure is not enough to stop the gravitational collapse, right? So the gravitational collapse will continue by overcoming the neutron, even the neutron degeneration. Now the problem is, now there is nothing to stop this gravitational collapse when this happens. So when there is nothing to stop the gravitational collapse, the star will be, contract and contract and continue to contract, and the density of the star will become extremely high. So this density will be an unusual number, even we cannot think about, right? Now, what happens is when you have this kind of dense object, even the light inside this object cannot escape from the inner region of this star, right? And these type of objects are what we called as black holes, right? So that now I guess you have an idea about what a black hole means, right? So it is again one of the extreme end states of these high mass stars. Now, the problem with the black hole, or the mysterious thing about the black hole, is that when you have these extremely dense conditions in a tiny volume, there are many unfamiliar phenomena that can occur in the region of these kind of regions, which are actually predicted by Einstein's theories of relativity. Now, this is why these black holes become so like extreme objects and superficial objects to people, because the phenomena that used to happen around the vicinity of black holes cannot be explained from the Newtonian physics in most of the time, because of the extreme dense conditions that you have. The space and time behaves in a completely different way around the vicinity of these black holes, right? Now, on the next day, we will look at what kind of these unfamiliar phenomena that could occur in these regions that are close to the black holes or in the vicinity of the black hole, right? And what Einstein have predicted from his theories of relativity about these black holes, right? So as the first step, we will actually learn a little bit about a very brief introduction about the special theory of relativity and the general theory of relativity. Once again, we are not going through equations and Einstein equations and everything, but we will very briefly mention those equations and get the idea what he has tried to explain to us about these curvature of space and time, and how those are related to black holes, and what are the phenomena that we can observe around the vicinity of black holes due to this high density objects or high density environment that we have, right? So that will be the starting point for us for the next lecture. Right, so we will talk about, the general relativity and what happens and how the matter curves the space and time and what happened to the light. And because of that, the things, consequences of the relativity and how they are related to our topic, which is about talking about the black holes, right? Like the time event horizon of a black hole, then those kind of things. So the next section will be basically about what is a black hole now, basically about understanding this Einstein's theory of relativity, especially general theory of relativity, which are kind of more related to this topic. And then once you understood the basic idea behind the Einstein's general theory of relativity, you can understand some of these unusual phenomena that happens around the vicinity of a black hole as well, right? So those two will go together, right? So we'll not specifically talk about like black holes, but we will combine it with Einstein's general theory of relativity, which will give you an idea about things that could happen around the vicinity of a black hole, right? Anybody have any questions up to here? So I'm going to stop the lecture at this point for today, because if I control that will be too much for you for one day. And so my plan is to conduct the lecture tomorrow, but tomorrow the lecture will not be in the morning, most probably. It will be at night. So I need to check the power cut schedule again, and I will schedule a time accordingly. So try to log in to the lecture at that particular time, right? So I plan to finish this section about the stars on the next day, which is most probably tomorrow night. And so there will be one section remaining after this section about the black holes, that will be about the motion of the stars, like how stars move on the sky, right? So that will be the last section for the stars. So I will try to cover this section plus that section in tomorrow. And then once we are done, we will move on to the section about the galaxy. So everything that we will be doing until tomorrow will appear in your second ICE exam, right? So that is my plan. Anybody have any questions up to here? So I will wait here for like 1 or 2 minutes if you have any questions. Otherwise, we are done with the lecture. You can leave, right?